Welcome back, everyone. This is Chapter 12 in Solutions, and we're doing the final section of this chapter as we're talking about the properties of solutions. We're going to see that solutions do some very interesting things. Specifically, they control how living things work, whether liquids go through cell walls. We'll see that as an application in anatomy at the end of the chapter. We're also going to see that physically they do a lot in terms of if you were to put some salt in your spaghetti water, the water boils at a little bit of a higher temperature and cooks the spaghetti faster. So the salt maybe seasons the spaghetti, but it also cooks it a little bit faster because the boiling point of water will raise just a tiny bit. You're also going to see that you will put a solution in your radiator of your car because you don't want water which freezes at 32 Fahrenheit or 0 Celsius. On a winter's day, there's lots of nights that it gets down to 0, and you don't want all of that water to be frozen in the pipes of your car and bust those pipes. So you add solutes to that in order to reduce the point at which that liquid freezes. You do the same thing when you put salt on the sidewalk. You're trying to make the ice that freezes at 0 actually freeze at 5 or 10 below 0 so that it has to be much colder for there to be ice on the sidewalk. If it's not 5 below 0, then even at freezing, that ice will melt and you can then walk on wet pavement rather than solid ice. So there's a lot of applications that we can make with these properties. But let's get started. We're going to see another concentration in this chapter. We've already looked at 3. We looked at mass, percent composition. We've looked at volume, percent composition. And we've looked at molarity. And now we're going to look at one last one. And all of these, of course, gives you a headache because you can't keep them settled in your mind. The molarity is the most common one. But molality is used, and it's used specifically in one aspect of chemistry that you'll never be able to get around. So I'll at least have to teach it to you. So to remember, solutions contain small particles, okay? And the particles are homogeneous or homogeneous, which means they're everywhere the same, mixed into any sample that you pick. You're going to get the same little particles floating around in the solvent, and we're using water most of the time. Okay, they're not separated by filters or a semi-permeable membrane. Okay, colloids is when you have bigger particles. All right. A colloid is not like Kool-Aid where you're going to have the tiny little sugar, tiny little water, and tiny dye particles. A colloid is going to have something bigger floating or suspended in the solution. So for that reason, since it's bigger, it can be filtered out. The good example of a colloid would be if you've ever seen the sun burst as a ray going through the clouds, and you can see the sunlight through, like a whole stream of sunlight coming through a cloud bank. The water molecules in the air are much bigger than the air. The molecules of gas in the air are so tiny compared to the water molecules that a cloud you can't see all the way through. It's not transparent. Kool-Aid, if you had a glass of Kool-Aid, you could actually see all the way through. It would be tinted whatever color the Kool-Aid is, but you could see somebody with their hand on the other side of the glass. A glass of milk, which has lots of blops of proteins and fats suspended in water, you can see light, maybe a little bit of light pass through, but you can't see anything on the other side of the glass. Those are colloids. They're large particles. They are uniformly dispersed. They can't be filtered, but they can be separated by semi-permeable membrane. So you could pour milk through a coffee filter, and you'd still have white milk in the jar underneath the coffee filter. But if you put it in a dialysis bag or inside a cell, like your cells are semi-permeable, then what happens is that the little holes in those membranes are so small that these big particles that are in, say, the milk or any colloid can't pass. So little things can pass, but big things are stuck. Okay, so let's look at some examples. Already said that anything you can't see through is going to most of the time be colloidal. So fog, that's water vapor. It's really big. Clouds, even sprays from the ocean. Like if you have ocean spray, you you wouldn't actually be able to. It's not transparent because the water is actually hanging out in the air temporarily. Dust in the air, chalk dust, smoke that kind of sits in the air. You can see light through it, maybe, but you can't see through it, and that's because these particles are big and they're hanging out in the air, and they might eventually settle out to the floor. Anything that you have a gas inside a solid, like a foam, like whipped cream or suds, are usually going to be opaque. If you can think, whipped cream you can't see, soap suds you can't see. Even though most of this is just air, you know what bubbles are, mostly air, but if you have a whole pile of soap suds in the bathtub, you won't be able to see through it. Okay. Anything else that's colloidal, where you have something mixed into something else, like olive oil mixed in with vinegar or lemon juice, or egg white, like mayonnaise, is going to be opaque. So homogenized milk, mayonnaise, butter, these are all colloids. Okay, cheese is a colloid that just basically solidifies before the big proteins fall out. Bigger than a colloid is a suspension, and a suspension will settle out. Okay, if you can think of a glass of dirty pond water, eventually all the dirt and rocks that are so heavy that it'll fall through the water and settle to the bottom of the jar, that's a suspension. For a while, you shake a jar with dirt and water in it, and you'll get muddy water, and for a while those little particles will kind of hang out, but they are heavy enough that they'll actually settle out. So you think, okay, you've got a solution which is homogenized like Kool-Aid, where you can see through it. Then you have a colloid, which is opaque, you can't see through it. And then you have a suspension, and a suspension also you won't be able to see through. Okay, so things like that would be blood. You've got platelets, you've got blood cells, you've got all kinds of stuff hanging out in that blood, and blood is not transparent. Okay, calamine lotion, that's the pink lotion you put on for when you're itching with poison ivy, and you actually have to shake the bottle because all of the solids will fall to the bottom of the bottle, and if you don't shake it, all you're doing is putting the water on you and you're not getting any treatment. All right, so these different types of mixtures will filter differently, okay? So you know that a solution will always go through a semi-permeable membrane and go through a filter. So filter paper won't take a solution because the particles are too little. A colloid, okay, a colloid will not go out of a semi-permeable membrane, but it will go through filter paper. A suspension can be trapped by both. A filter paper can trap a suspension. If you were to say put boil coffee in water, and you just have boiling coffee in with water, and you pour it through a coffee filter, and that's what you're doing when you put hot water in coffee filter in the coffee. You've got a brew of coffee and water. Well, the coffee sticks to the filter paper, and the coffee pours through. The coffee is a solution, and it's possible that the coffee actually could be a colloid. If sometimes you can see through coffee, but nice dark coffee you probably couldn't. It would be too opaque. Okay, so a solution is not filtered by either. A colloid can be filtered by a semi-permeable membrane, but not filter paper, and a solution can't be filtered by either. Here's an example, just in a table form. You can look at this later. Okay. So the number of moles of particles in water depends on the type of solute. Okay. Now we've looked at this a little bit. If you have, put this in your mind, if you have sodium chloride, which is table salt, and you put it in water and it's a strong electrolyte, it'll break apart into positives and negatives. So if you have something like sodium chloride where you have one positive and one negative, when it breaks apart, you've got water plus two types of ions there. If you have something like H2SO4, sulfuric acid, where you have two positives matching with one negative, since it's a strong electrolyte, you put it in water, it's going to break apart into three ions, two positive H's and one negative SO4. Okay, so if you have a non-electrolyte, say sugar, that doesn't break apart into positives and negatives, you put that in water, all you're going to get is the water and the sugar. Okay, so you'll have one dissolved particle. If you have salt where there's a positive and negative, you'll end up with two dissolved particles. If you have a salt where there's two negatives and one positive, or two positives and one negative, or something else, you could have 3 or 4 different particles dissolved in that water. So the number of moles of particles depends upon what type of a solute it is. Okay? Non-electrolytes are going to always form one particle for every molecule that it was, because it doesn't break apart. So it's always going to have 1 mole of particles. Okay? But a strong electrolyte can break apart into 2 or 3 or 4 or however many complicated sets of positives and negatives that gives you. Okay? So here's an example. A mole of sugar, okay, if you put a mole of sugar into water, you're still going to have a mole of sugar because it doesn't break apart. If you have a mole of potassium chloride, which breaks apart as 1 positive, 1 negative, you put that in water, you're going to have 2 moles of particles, okay, in the water. How many moles are dissolved in the water? 2 moles of particles, because you're going to have 1 mole of ions that are positive and 1 mole of ions that are negative. Okay, if you put in 1 mole of salt, you're going to end up with 2 moles of particles dissolved in the water. So what's dissolved in the water can determine a lot on how many moles of stuff is actually in that water. Okay, we'll look at a lot of examples for this. So here's your last concentration. Concentration is called molality. It's again moles, but it's moles of solute, not over liters of solution, but over kilograms of solution. So it's kind of like that mass thing that we looked at earlier in the chapter, only this kind, it's in how many kilograms of solution there is. Because we're going to see that it has to do with, so 1 kilogram of solvent. I'm a little confused. I think it's solvent. I'll see it in a second. What is the molality of a solution containing 80 grams of a non-electrolyte glucose? Okay, so we know that we've got 1/4 kilogram of water and 80 grams of glucose. So we need to know how many moles it is because it's moles over. Okay, so we have 180 grams equals a mole of glucose. So we're going to have 0.44 moles, and you're going to have a kilogram of the solvent. Let's go back because I think there was a mistake here. This is a mistake, okay, and I will fix it. Okay, this is kilograms of solvent. I wrote it wrong. I'm sorry. Let me show you why that's important. Molality is moles over not the whole solution, but how much solvent you have. Because the more that it breaks apart, the higher that type of concentration is going to seem. Okay? It's not how many moles of the material that you have, it's how many times that it breaks apart. Let's imagine that I have a Lego wall that's built out of 100 Legos. Okay? every wall will have 100 Legos. So if I break them all apart into Legos, then I have 100. Well, let's say you build a wall that's got 300 Legos in it. It's one wall, but it's got 300 Legos. If I can break something into smaller amounts of pieces or more pieces, and I'm looking at how many pieces are in it, that's a kind of a concentration. What's the concentration of dissolved particles? That's what molality is, okay? And that's what's going to affect boiling water or freezing water or other things that we talked about before, these applications. It's how many things does it break apart into, not how much that you have. That's why molarity is the most common, because you just want to know how much you have. That's why it's really easy. Everybody can do it. This is a little bit harder because you're going to have to say, what kind of stuff do I have breaking apart, and how many things is it going to break apart into? So I don't want kilograms of solution. I want kilograms of solvent. How much water do I have, and then how many moles of different types of particles am I going to have inside that liquid? Okay. So let's look at what it does. You can change the freezing point. Okay. The freezing point depression is, the little symbol for it is delta TF. That's the freezing temperature. So the temperature at which it freezes changes, that's what delta means, 1.6 degrees Celsius for a 1 molal solution. So if you add some solute to the water and you have a 1 molal concentration based upon what it breaks down, you can change the temperature 1.86 degrees. So it will actually freeze not at 0, but lower than 0 for every amount of water that you have like that. Boiling point is the same. For a 1 molal solution, the boiling point elevates 0.52 degrees Celsius. So instead of boiling at 100 degrees, it'll boil at a higher temperature, okay, just by putting something in the material. Okay. So the effects of solute. So for a non-electrolyte, 1 mole of particles, the lowered freezing point just goes down 1 unit, which is 1.86, okay? And the raised boiling point is just up 1 unit, which is 0.52, okay? If you have a strong electrolyte that breaks apart into 2 particles, then you're going to have not 1 mole of particles in the water, you're going to have 2 moles of particles in the water, which doubles the freezing. So it doesn't go down 1.86, it goes down twice that, down to 3.72, and it doesn't go up 0.52, it goes up twice that to 1.04. So adding, say, sugar in your antifreeze, where the antifreeze goes, sugar water is better than water. But if you could pick something that would break apart into lots and lots and lots of different particles, then you could raise it even more. And that's what it is that you put in. That's the antifreeze that you put it in. It's called antifreeze, but it's also anti-boil. The antifreeze you put in your radiator lowers the temperature that it freezes at, but it also raises the temperature it boils at, because it has so many different particles broken down in that same amount of liquid that it raises the temperature that it boils at, and usually the car can handle it. It would have to be a very, very hot day in the desert before your car actually boils over. I've had it happen once, I think. Okay, so in this case, calcium chloride breaks apart into 1 positive and 2 negative, so that's 3 moles. So you're going to take the 186 and triple it. You're going to take the 0.52 and triple it. Okay, so that's where that's coming from. Here's the application in anatomy. Osmosis is when water flows from a high concentration to a low concentration. Okay, and what I mean by high concentration, it's high concentration of water. So if you have high concentrations of water, that means you have low concentrations of dissolved particles. So low concentration of solute. So it goes from high concentration of water to low concentration of water. The level of the solution with the higher solute rises. okay, because the water is coming from high concentration where there's a little bit of solute, and it's moving across the semipermeable membrane into an area where it's got a lot of concentration of solute. So it's a lower concentration of water. Water goes from high concentration water to low concentration water. What happens is the water rises on that side. So the more solute you dissolve, the more that the water rises. This is actually how that you can get water to rise all the way up a 200-foot tree. Okay? If you put a drinking straw in a glass of water, that water might climb up the straw a tiny bit higher than the level of the water in the glass, but it's not going to climb 200 feet. But if you can start adding sugar to the inside of the straw, not into the glass, but the inside of the straw, then water will move from the glass into the straw and rise up the straw. And that's how it's happening in a tree. This is called osmosis. So the concentrations of the two solutions become equal. Eventually, the same amount of water concentration is the same inside the tubes, the xylem and phloem tubes, and inside the groundwater. Eventually that happens. But since you've got more dissolved stuff in the tree, the water climbs the tree. Okay, I hope that makes sense. I need to draw you a picture. Okay, so here's an example. If I've got 10% starch on the right and 4% starch on the left, I have more pure water on the left. The light green has more water in it. So high concentration of water goes into low concentration of water, which means it goes into the higher concentration of solute, and eventually the water level on that side of the semipermeable membrane rises. Okay, that's called osmotic pressure. The pressure that's being shoved down because this water's piled up essentially is called osmotic pressure. That's what this is. It's produced by the solute particles dissolved in a solution, and it's the pressure that prevents the flow of additional water. Eventually, the same amount of water on both sides, even though they're at two different levels, the same concentration of water is here, and the same amount of concentration of water is here because I have the water comes in and out and in and out. Okay. In red blood cells, okay, there's more stuff inside the red blood cell than in the external outside the red blood cell. Then what happens is you've got higher concentration of water outside, then water will move in. If there's higher concentration of water inside the red blood cell, then it'll move out. So if you don't want something to happen to your body cells, you need to have a fluid around those body cells that has the same amount of water, same concentration of water inside and outside. Okay, so if you have isotonic, iso means the same, it exerts the same osmotic pressure. There's not the same amount, but the same concentration of water on the outside and the inside. So water moves in, water moves out, and there's no change in the shape. If you have a hypertonic solution, this is hypotonic solution means there's less dissolved stuff outside, higher concentration of water outside, so water will move into the cell, only a little will move out, and eventually the cell will keep getting bigger, 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 and explode. It will pop it. And then the other possibility is that you have a hypertonic, you have more dissolved substances outside. That means you have a higher concentration of water inside, and the water leaves out of the cell, and the cell shrivels. Okay, it crenates. It's called crenation. It shrivels and basically becomes like a raisin or a prune. Okay, so if you were to say put pure water in your bloodstream, okay, with no dissolved stuff in it, if some well-meaning nurse were like, hey, he's dehydrated, he needs an IV with some pure water, what would happen to poor O'Brien is that all the water that she put in my blood would be higher concentration than my cells. And all that water would go into my cells and explode all of those cells. They would all die. If she put something that had less concentration of dissolved substances, there was more dissolved substance, like heavy sugar, like pure syrup. If I just put maple syrup in my veins, well, there's a little bit of water in maple syrup, but a lot of goop. What would happen is there'd be more pure water in my cells, and all that water would come out of the cell, and all my cells would shrivel. So what you do when you go to the hospital is they give you an IV of isotonic solution, which has the same concentration of water as you have in your cells, and your cells are nice and happy. Okay? Dialysis, this is how you clean somebody's kidney or their blood when their kidney doesn't work. Okay? Solvents and small particles can go through, but large particles can't. Okay? So what happens is that it forces the little stuff out of the blood into the dialysis tubing, and then it's flushed. That way you're actually cleaning someone's blood. Otherwise they would die. They would get all kinds of problems and die very quickly if you didn't have your blood cleaned. That's what your kidney does, is cleans your blood. Hemodialysis, your blood is actually removed from you. You have some sticks, or it sticks into your veins. The blood comes out into a tube and into a machine, and then the water inside and outside the machine will come in and out, into the inside and out from the inside, and eventually what's left is just the yucky stuff that's then flushed at the end, and the person doesn't die. Really long lesson. Sorry about that. I'll see you in class.